Hello, everybody. And now we're in section 2.3, and this is the subject of continuity. So continuity is kind of like, what you imagine it to be. If I have here's a line which is just one continuous, I don't have to take my pencil off the paper, so this is continuous. This here is continuous until I hit that little empty point there, and then it's discontinuous right there when x equals 2. But then it goes back to being continuous, afterwards. And here we have a function they call a step function. It's continuous down here, and then it jumps, and now it's continuous up here, but it's not continuous when x equals 0. So that's a very simple, continuity. And of course, here's another example. This function is continuous because it's all, one, I don't have to take my pencil off the paper. This is clearly discontinuous because it jumps here, jumps there, jumps there, just jumping all over the place. Now each little contiguous, segment that interval is continuous, but the overall function is not continuous. I should have said that over here. See, in this guy over here, the interval from negative infinity up to 2, up to but not including 2, that's continuous. And the interval from 2 to positive infinity is continuous, but the overall function is not continuous because of that one teensy weensy little hole. And it's so microscopically small you can't even see it, yet it ruins the whole continuity of the function. And similar here, this function overall is not continuous. Yes, it's a continuous piece down there and a continuous piece down there, but since they don't connect, it's not overall. Notice the similarity with that in limits. Just like limits, to have an overall limit, the two sides have to connect. To have overall continuity, the two sides have to connect. Kind of interesting comparison. Now let's take this common sense and put it into fancy language. Let me just move my. I don't know if you can see it. I'm not sure if you can see it. So a function is continuous at the point x equals c if there are three things you need. The limit as x approaches c of f of x has to exist. You can't just have an empty circle with no thing. F of c has to exist, but not only does it have to exist, but it has to equal the limit of the function value. So let's see what I mean by that. See over here, f of, what is that, -4? F of -4 exists, but it's not the limit as x approaches -4 from the negative side. You see what I'm saying? Now, let's look over here. When x equals, 3? When x equals +3, the f of +3 exists, is that dot right there, but it's not equal to the limit as the function approaches 3. So that's why you need this third condition. So a function is continuous on an open interval a comma b if it is continuous at each point on the interval, and if one or more of the three conditions fail, then the function is discontinuous. So in other words, in order for a function to be continuous, you need all three of these conditions. That is the way that is that. Now over here, let's see. So here, the function is not defined, but x equals -2, excuse me. And here, the function jumps, and plus is not defined, and that's the story. Okay, let's continue here. And again, I'm looking at the textbook here, and you can get this all in Math Excel. Let's look at the let's look at this graph right here. So it is not continuous in x equals -3. It's not continuous over here. It's not continuous here. It's not continuous there. Well, let's just analyze what is the thing. So here, this violates the idea that f of c has to exist, because it doesn't exist. Here, f of c does exist, but it's not equal to the limit, at least not equal to the right-handed limit. Here also, f of c does exist, but it's not equal to the now this is interesting. This function, this does have a limit as x approaches 2, but it's not continuous at x approaches 2. Because when I come from the right or come from the left, the limit of the function is 5, the y value. But the function value is not 5. The function value is 3. So that's what that is. And here, of course, this fails on a lot of counts. One is that the function does not, the f of c does not exist because I have open circles here. The limit doesn't exist. Boy, this is like racking up the points here. And the function value is not equal to limit. There is no limit, so what can I say? This is a big mess up over here. Alrighty. And let's say we have equations here. F of x equals x plus 2. Well, if x equals 2, just plug it in, and you see it works, no problem, it's continuous. This is not continuous when x equals positive, x equals 2, because if I plug 2 into the bottom, I get this guy here. This is going to be a hole, by the way. This is going to look like, the graph of this is going to look like this graph over here, but it will not be continuous when x equals, when x equals positive 2. And why do I say it's going to look, why do I say that B is going to look like A? Because if I factor the top of B, I get x plus 2, x minus 2. The x minus 2s will cancel, and I just get y equals x plus 2. So it's going to look like graph A, but there'll be one microscopic point that's missing. What a shame. And this one here, this is continuous when x equals 0, because h of 0 is the this is not continuous when x equals 0, because if I plug 0 in, I get the absolute value of 0 divided by 0, and that's not defined. And the limit as x approaches 0 of h of x also doesn't exist, similar reason. And h is continuous, but it is continuous when x equals 1, because there the limit is just 1. So that's the way this works. And that is the very fascinating story. Now let's take a look at. We define continuity on an open interval, but it can be, as you see, it can be continuous on a closed interval. This is the closed interval from -1 to +1. And this is a little semicircle there. And this is like sort of a half parabola. And this is continuous on the half closed interval 0 to infinity. In other words, if the infinity part is open, but infinity always gets parentheses, always up, because as I said, infinity is not a number, it's just like a direction you go towards infinity. So it's always round brackets. Whereas, but this function is defined for 0, so it's closed on that side. That's why I say it's half closed, closed on one side, not closed on the other side. Now, if two functions are continuous on the same interval, then their sum or the difference or the product or the quotient is going to be continuous, as long as the bottom doesn't equal 0. For quotient, I'm talking about. If you have a function that's constant, well, it's continuous for all values of x. It's always defined. It's always, I mean, it's And if you have a function x to the nth power, that's also continuous for all values of x. In fact, any polynomial function is continuous for all values of x. Let's continue. A polynomial function is continuous for all x, like continuous for all x, any polynomial function. A rational function is going to be continuous for all x except for the values that make the denominator 0, because those are the problem points. Other than that, it'll be perfectly defined everywhere. If I have a root function, that will the root of a function, that's going to be continuous as long as the inner function of f of x is continuous. And if I have a if the root is an even root, that, by the way, E was for odd roots. If the root is an even root, then I just have to throw in the condition that f of x has to be non-negative. Because if f of x is negative, then it's it'll be undefined, and it'll be up. You get the point. Okay. Let's see. So A is a polynomial, so it's continuous. B is a rational function, so it's continuous except for -2 and +3. C is the cube root of some polynomial, so therefore it's continuous everywhere. D is the square root of x minus 2. So as long as x is greater than or equal to 2, this will be continuous. But if x is less than 2, then it becomes the square root of a negative number, and that messes everything up. What can you do? Alrighty. Now, sign properties, because if you have property, you may as well put a sign up. Theorem 2 here is basic. It's kind of common sense. If f is a continuous function on this interval AB, and f of x never equals 0, so that means it's either going to be all positive or all negative. It means it's either all going to be above 0 or it's all going to be below 0, because if it's continuous, it can't, and it never equals 0, it can never cross the 0, and that's basically what we're saying here. And this actually helps solving many types of inequalities. So for example, suppose I have x plus 2 over x minus 2 equals greater than 0, something we've seen in algebra. So, whoops. So I let f of x equal x plus 1 over x minus 2, and the denominator is equal to 0 when x equals 0. So that's the bad value. The top is equal to 0 when x equals -1. So it's discontinuous when x equals 2, and it equals 0 when x equals -1. So that means if I break this up into 3 intervals, -1 and +2, this is where -1 is the value that made the top 0, and +2 is the value that made the bottom 0. So I look at these 3 separate intervals now. So I take a test point from each interval. If I get one positive answer, if I get one positive value, it means the function is positive this whole way through. If I get one negative value, it means it's negative the whole way through. If I have one positive value here, I get a positive the whole way through. So I could just take 3 points, and from those 3 points, that tells them the entire function, where it's positive and where it's negative. That's pretty cool and awesome. All right, well, that was loads of fun. Let's move on. Now, a real number x is called a partition number, or a function f, if f is discontinuous at x, or if f of x equals 0. This is just similar to what we did in the previous problem. Just so in this case, -1 is a case where f of x equals 0, and +2 is the example where f is discontinuous because it's undefined at x equals +2. So so partition number is just a way to describe what we did before. This is just summarizing this is a good thing to read. This is just summarizing how to figure out positive and negative based on those charts that we just had. And let's look now at some business, always business, more business. So positive profit. See, in this problem, they're going to show us p of x equals 6x minus 0.001 x squared minus 5,000. This function here, p of x, is what they call a profit function. Now, when it's positive, that means you're making money. When it's negative, that means you're losing money, because a positive profit means you're making money. A negative profit means you're losing money. So we want to know, when is this function here going to be positive? Well, if I want to find out it's never undefined because it's a straight polynomial. So I just want to find out when this equals 0. Well, I could take this function here. I could factor out. I'm pulling out -0.001, just that constant, because that's the coefficient of x squared, which is the largest power. Now that allows me that allows me to factor, and I get my original function p of x is going to be -0.001 times x minus 1,000 times x minus 5,000. So 1,000 and 5,000 are going to be the partition numbers. Now I just got to do a test. When is it positive? When is it negative? So if you just take some samples, you'll see that when x is less than when x is in this region of less than 1,000, that's where it's negative. When it's in the middle region between 1,000 and 5,000, that's where it's positive, and in here is where it's negative. So it's in this area here that x is up. And that's really interesting, by the way. Personally, I just find it interesting, just the business end of it. X is how many loaves of bread you make. So you see, if you make too many loaves, or if you make too few loaves, you're going to lose money. But if you make just the right amount of loaves, you're going to make money. Now, when I say just the right amount, I mean, between 1,000 and 5,000. Now, suppose you want to find out the precise amount that makes you the maximum profit, not just know that, well, somewhere between 1,000 and 5,000. Yeah, well, that's a pretty big range, So how much bread should I make? Well, to get the most bread. Hi, see what I did there? The answer is we're going to learn using calculus how to figure out an exact amount, exact point where it's the optimal profit, the maximum profit. It's somewhere in this range from 1,000 to 5,000, but we're going to use calculus. Again, we're not going to do it today, but we're going to get to that. And these are some of the exciting things that we're going to be able to do with this section. Anyway, that is the end of section 2.3. It's been loads of fun, and we'll see you guys next time. Bye, everybody. This is, I see Dumbledore coming. I got to go. Bye. Snape, no, Snape.